but Christian finally somehow figured out how to let me in, and so here we go. So I'm going to talk about reliability disasters today. This has been a subject that's been of high interest to me for very many years. And part of it arises because of my interest in reliability, and also because I've been involved sometimes in the aftermath of some of these reliability disasters. So here's an overview of my talk. I'll first define reliability, and then talk about a general problem, a common problem, one that I've seen arise over and over again in companies having to do with reliability problems. And then I'm going to just flash one slide that lists a whole page full of reliability catastrophes, most of which everybody knows about. And these are the kinds of things, both kinds of these things are things that we want to avoid because of the difficulties that they cause. Then I'm going to go through and talk about 5 particular examples that are well documented in the literature, and as I mentioned, in a couple of the examples, I was involved in the aftermath of trying to track down what happened, what could be done to prevent these problems in the future. And then I'll end with some concluding remarks indicating what we've learned from this. Okay, what is reliability? There are different definitions. So the one that Luis Escobar and I used is this one here. Basically, reliability technically is a probability. It's a probability of surviving a certain mission time. But reliability is really much broader than that. Lloyd Condra said that reliability is quality over time. So that makes an interesting connection between quality and reliability. In some sense, high quality is a prerequisite for high reliability. Failure avoidance is often the way engineers think about reliability. Indeed, I think I first learned this from Tim Davis because of his involvement in reliability. And so you know that there's a potential failure mode, you figure out how to design your product to avoid that failure mode. Also, reliability is a highly quantitative engineering discipline. Statisticians are often involved because the quantitative side of reliability requires statistical and probabilistic methods. Okay, so here's the common problem that I've seen over and over again. A product is introduced into the field, and before too long, a small number of early failures are detected. Often, the failure mode is unanticipated, or if the engineers anticipated it, they said, oh, that's not really going to happen. We don't need to worry about that. But more common, they didn't even think about this particular failure mode, and so they didn't design to avoid it. Okay, so after these early failures come in, then the questions start arising. Questions coming often from management wanting to know, how bad is this problem? And technically, the first question is this a problem that's affecting just a very small part of our product population? Or is it the case that every single unit that we've put into the field is going to fail prematurely? So there's a big difference between those two. And often you have to go in and do engineering analysis combined with field data, sometimes a survey, to figure that out. And if it turns out it's only a subpopulation that's susceptible, then the question is, can we identify those and perhaps mitigate those failures? And then kind of a secondary question is, how fast will they fail? Because that will tell you where you need to place your effort to try to prevent failures from occurring in the field. And then the next question is, what's the risk? So again, management's asking, what risks do we have? And in particular, they're concerned, for example, with warranty costs, because they have to put away cash reserves to cover any potential warranty cost. In many cases, or in some cases at least, there's a question of, is this a safety issue where we might have to have a recall of our product? And then there's the question, how do we fix the problem for maybe the next generation of our product? And also, how can we avoid similar problems in the future? One common element is that the reliability problems that arise often are due to multiple mistakes that are made. And we'll see that in some of the particular examples that I'll go through in this presentation. Okay, so I'm not going to read this, of course. This is just a list of well-known single event catastrophes. Again, these are all things that most people know about because they're very famous. And most of those can be traced back to some kind of a reliability problem. Today, I'm going to talk about 5 particular problems that I've studied over the years. And as I said, in a couple of cases, I was involved in the aftermath of the reliability disaster. And all of these are well documented in the literature, even though I was involved with a couple of them as I wrote up this talk and then a corresponding paper. We were careful to only present things that are well documented in the literature. My first 2 examples have to do with accelerated testing. That is, accelerated testing was involved in the product design. The basic idea of accelerated testing is to get reliability information quickly by testing at high levels of certain accelerating variables, like temperature. And the idea is that then we can see failures in a reasonable amount of time. And then we can, as you can see in this diagram here, we can extrapolate back down to use conditions. So in this case, units were tested at 80, 100, and 120 degrees C. And then the extrapolation was done back to, say, 50 degrees C, which would be the temperature during actual use of the product. I've been involved with accelerated testing my entire career, and it's a very dangerous kind of game to play, but it's something that engineers have to do because they want to design a product to last, say, 10 years, but they can't test for 10 years. Often they need to compress the testing down into a period of months, if not weeks. So my first example comes from AT&T back in the started back in the 1970s. And at Bell Laboratories, which was the research arm of AT&T back then, they designed a revolutionary new lead acid battery, which was sometimes called the Bell cell because it was the Bell system, as we called it back then. And the idea of the Bell cell was to use these disc-like plates of lead instead of the rectangular plates that had been used traditionally in lead acid batteries. And the engineers believed that they could extend the life of the battery by almost an order of magnitude. And so they designed this battery. And before too long, they had hundreds of thousands in service during the 1970s. However, in 1978, they suddenly discovered that there was a serious unanticipated failure mode where the positive post in the lead acid battery was corroding. And they did a survey, and the survey showed that about 30% of the batteries, so they had a failure. And then they decided they needed a survey to figure out how bad is the problem. And after the survey was conducted, they discovered that about 30% of the batteries had this serious corrosion. And then they had to figure out the problem and figure out which ones to replace first and so forth. The root cause was an incompatibility between an epoxy seal that they had around the posts that were to lower maintenance cost by not letting the corrosive elements come outside of the battery. So ultimately, a very large proportion of these cells had to be replaced. What went wrong here? Well, as it turns out, the engineers didn't anticipate this failure mode, so they didn't test directly for it. And indeed, the accelerated tests that they did do, which was focused on the life length of the plates, actually inhibited the corrosive failure mechanism. That is, they were testing at higher than use voltage, and that higher voltage actually caused a deceleration of this serious failure mode that ultimately caused all of the problems. So accelerated tests can be misleading and will often miss unanticipated failure modes because you're not focusing on them. And as I said, in this case, their accelerated test actually inhibited the serious failure mechanism. So it's really important for engineers to anticipate all of the different causes of failure and then take steps to prevent those failures from occurring. Again, failure avoidance. If you do proper upfront experimentation, you can generally get the knowledge needed to design a high reliability product. My next example comes from General Electric. And I've had a long association with General Electric going back to when I was an intern there when I was in graduate school in the mid-1970s. But I was not involved in this problem at all. Everything I talk about here was in this Wall Street Journal article that was published. So what happened here? In the early 1980s, GE was losing market share to its competitors, particularly offshore competitors. And Jack Welch had just become the leader of General Electric. And he basically went around and told all the different GE companies at that time, I don't want you to be involved in commodity products anymore. I want you to be number one or number two in your field, or I'm going to sell you. And Jack sold off a lot of parts of GE. Well, the people at GE Appliances said, we need to get going here. And so over the period of time, 1983 to 1986, they designed a revolutionary new type of refrigerator. And one of the innovations was to use a rotary compressor, which would be lower cost and higher efficiency. They also had other innovations, like this particular refrigerator model was the first one where you could get ice and cold water without opening the doors, something that's a fairly standard feature these days. So they did all the usual things, including running an accelerated test where they tested a very large number of these rotary compressors. And they tested for 1 year and they saw no failures. So a decision was made to launch the product. And by 1987, they had more than 1 million of these units in service. However, 1.5 years after the first units were put into the field, they had their first failure. And they went out to study what happened with this failure. And it turned out that the failure occurred in Philadelphia, Pennsylvania. And when they investigated, they found out that this refrigerator was in a closet. Now, you don't want to put a refrigerator in a closet because you need ventilation to get rid of the heat. So basically, it was like a 1.5 year accelerated test, and then they had a failure. Not too many weeks later, they had their second failure. They went to investigate the second They went to investigate the second failure. It was not in a closet. It was in Puerto Rico. Puerto Rico is a warm place where refrigerators probably have a pretty heavy duty cycle, but refrigerators have to be able to survive in that kind of an environment. Then they really got serious about the failure mode and said, what's going on here? Well, it didn't take the engineers long to discover that virtually all of the units put into service would fail prematurely because of a serious difficulty. It turned out to be a difficulty, a lubrication problem that they had. So when they discovered that all of these were going to fail, then the next question was, what do we do? And GE made the right decision. They have a very strong reputation for high quality, high reliability. So they proactively attempted to replace all of the compressors before they failed. So GE was calling up the customers and saying, we need to come replace your compressor or fix your refrigerator. And the customer says, oh no, it's working fine. But they said, no, we have to come out and replace this. So that's what they did. And it cost the company almost $500 million, which is a huge amount of money even today. But back then it would have been enough if GE Appliances had been a company by itself and not linked to GE. They would have gone bankrupt. They just couldn't, no company could afford that kind of loss. Okay, so what went wrong? What caused this to happen? Well, it turned out that they rushed to market without sufficient reliability testing. After the accelerated test was over, the engineers did what they should have done. They took apart the compressors and inspected them. And they discovered that there were indications that those units, although they had not failed, they were very close to failing. And they traced it to this lubrication issue. But that information did not float upwards, and they released the product anyway. It was just lack of bad communication. It was well known within GE and outside of GE that when there was bad news, people tended to get fired under Jack Welch. And so the bad news did not float upwards. So it was a serious communications problem. And so there really were barriers to information flow there. And so the information from the engineers didn't get high enough in management to prevent product release. Okay, my next example is another very well-known reliability disaster known as the Challenger Space Shuttle failure. So there was to be a launch on January 28, 1986. And all of these launches were very highly publicized, at least here in the United States. But on the evening of January 27th, the night before, there was a long 3-hour conference call between NASA and Morton Firestone, who was the manufacturer of the rocket launchers. And the problem was, the concern was that the engineers said there's high risk here of a failure because the temperature is going to be so cold tomorrow. The forecast, and this is in Florida where it doesn't usually get that cold, but it was going to be that cold that day, was to be something like -1°C. They had never launched at that low a temperature before. The previous lowest temperature was 12 degrees C. And most of the launches, because Florida is a warm place, the temperature was between 18 and 25 degrees C. Richard Feynman, the famous physicist who was on the committee that studied this after the fact, he learned that estimates of risk from the engineers were 1 in 100, but estimates of risk from management were 1 in 100,000. A huge difference there. One has to ask, where was management getting their information? Well, it wasn't from the engineers. So that was never reported, how they came up with respectively, how they came up with those numbers. But after, on this 3-hour call, after discussing the data, there was a very strong recommendation from the engineers not to launch. But there is an enormous amount of pressure that came from NASA management to let us do this. And so the managers at Morton Thiokol eventually agreed to allow the launch. Subsequently, in the aftermath, a careful study was done of all of the data that was available. And this is a paper that was published in the Journal of the American Journal of the American Statistical Association, JASA. And in this paper, after a very careful risk analysis, they concluded the risk was more like 1 in 8. So much higher than even what the engineers were predicting. And the problem was that the engineers weren't looking at the data correctly. So here's a cartoon of the space shuttle, and the arrows there are pointing to the field joints. There are 6 of them. And the failure occurred here at this one. Now, each of the field joints has 2 O-rings. If one O-ring fails, it's not a problem. If both O-rings fail, that leads to a catastrophe. They had never had 2 O-rings fail before, but they had had quite a few O-rings fail in the past. So this is a quote from the so-called Rogers report, which studied this very, very carefully in the aftermath. So I won't read it, but basically 2 O-rings failed, and because 2 O-rings failed, there was a gas leak at the field joint, which caused the catastrophe. Okay, so I've already said this. And so they had 2 O-rings fail, and that's what led to the catastrophe. Here's some photographs over time. In the first one, you can just begin to see this little plume. That's the failure of the O-ring. And so that led to basically a kind of structural failure of the rocket motors, as you can see as you look at the photos going from left to right over time. Here's the data that the engineers were discussing in their 3-hour phone call. So that's what they were looking at. No plots, just a table of data that had been faxed back and forth. And then the engineers and the management are all on this phone call, and they're discussing these things, trying to decide what to do. If they had plotted the data that they had in front of them, this is what they would have seen. So what we're looking at here is temperature on the x-axis and number of events, that is number of O-ring failures on the on the vertical axis. So you can see that they had one time they had 3 failures, but they were failures in 3 different places, 3 different field joints. So it was not a catastrophe. But notice the temperature where that had occurred was the 12 degrees C. And that's what the engineers were thinking about. But then there was disagreement saying, well, look, there doesn't, we had failures all the way up to 60, 70 degrees. However, what they completely ignored, oh, and this is the extrapolation. So I just extended this down to 0 degrees C, which was roughly where the temperature would be at launch time early in the morning. So there's no data down there. But the biggest thing that the engineers and managers ignored was the extensive data that they had with 0 events. So when you go from the top plot to the bottom plot, you can see these extra events here. And as soon as you look at that part of the data in combination, then it becomes abundantly clear that temperature is a really important factor on the failure of the O-rings. And also, as was pointed out, just basic knowledge of physics would also have suggested this. Namely, failures of O-rings tend to occur when they get brittle. When we know that certain materials like that age over time, they become more brittle, they become more prone to failure. In this case, they become brittle because they are at such low temperatures. In fact, there's the very famous experiment that Richard Feynman did at a committee meeting when in the Presidential Commission, where he took an O-ring and he put it into a glass of ice water. And then he pulled it out and hit it with his pen, and it shattered. So basic physics should also have suggested that this was a very dangerous thing to do. Okay, so what did we learn here? Engineers knew it was risky, but they didn't have the technical and statistical tools to convince management, unfortunately. Use of proper graphical methods, like the bottom plot on the previous slide, would have made it clear that low temperature was an important risk. And they should have used all of the relevant data. So I often see this from naive people analyzing reliability data, where they focus on the failure times of the units that failed and ignore all the ones that didn't fail. And I think another thing that we learned is you really should be concerned when management overrules what engineers are suggesting. Okay, my third example is another very famous reliability disaster known as United Airlines 232, sometimes also called the Sioux City Accident. This arose in 1969, where a DC-10 was flying from Denver to Chicago. And when they got over Sioux City, Iowa, about 3/4 of the way there, they suddenly had what's known as a catastrophic disk separation. What the pilots knew is that they lost, that there had been an explosion in the tail engine of the DC-10, and they lost all hydraulic control. Now, the DC-10 was designed to have triple redundant hydraulic system, meaning that there were 3 separate hydraulic systems. If one hose broke, the other 2 would be fine. And so the idea is with triple redundancy, you would never have a failure of the hydraulic system. Unfortunately, all of those hoses were routed together. And when the disk separation occurred, which is basically an explosion of the engine, disk separation is kind of a euphemism, it severed all 3 of the hoses simultaneously. So these were not independent events, of course, and that's where the theory of redundancy sort of falls apart if you have that kind of dependency. As it turned out, there was an experienced pilot who was a passenger, but he told the pilots of the plane, "I think I know what we can do." And basically what they did was they could steer the plane by adjusting the thrust in the two remaining engines. And they were able to have a crash landing of the plane. A number of people died, but there were a lot of survivors as well. It was really rather miraculous that they had some survivors here. So what was the problem here? Well, all of the details of this are in an NTSB report that's publicly available. But here's a picture of the DC-10, and again, it was the tail engine that exploded and severed the hoses that were going to the rudder and the other things that are controlled with hydraulics near the tail of the aircraft. And here's a picture of the front of the engine. What we're looking at here on the right is the stage 1 disc, the front disc in an engine. So you've all looked at the front of an aircraft engine. You see these blades. The blades are slotted into this disc, and it was this disc that it literally exploded. The root cause was what's known as a hard alpha. It's a brittleness in the titanium alloy. And so the reliability modeling is based upon the assumption that we don't have any of these material anomalies. And engineers know that these things can arise, and so they inspect for them, but they missed this one. They did not see it. Moreover, the disc had been inspected while in service as well, where basically periodically they take the engine, break it down, and do an inspection to see if there might be cracks there. Because cracks will initiate and grow in these discs. It just takes a long, long time for them to initiate, and they grow very, very slowly, unless there's a brittleness, a material anomaly. And what happened was the crack reached the hard alpha, and it went very rapidly and caused the failure. So again, there had been multiple inspections on this disc, but it was never detected. Now, this was 1989. I can tell you that during the 1990s, so again, I was involved partially in the aftermath, there was a huge amount of research that was done on how to improve inspection capability in what's known as non-destructive evaluation. And I was involved in some of that work. Turned out there were also problems with GE's manufacturing inspection and also the inspection that was done in service. But again, that has been improved tremendously today. There's also some other anomalies in the maintenance processes and other things that were discovered when this very careful investigation was done. And you could argue that the McDonnell Douglas design of the triple redundancy hydraulic system was flawed. So again, the accident led to many improvements in both manufacturing and inspection. So what did we learn here? Quite a few things, as it turns out. There needed to be improvement in inspecting aircraft engine parts. Especially the discs. And if you read the recent news, there's been some engine failures. Those have been in fan blades. Supposedly, if a fan blade fails, it's not going to be catastrophic, but it has been for the engine at least. And so those can be serious too if the blades are these big blades. Need for better design sources of power for both flight and engine controls. That would be the hydraulic system. Better long-term record keeping, because there were some serious problems with the records that had been kept, as I said, by both GE and United Airlines. And they started a worldwide database of engine part failures because there wasn't any data. They know failures like this had occurred before, but there was no source of data. But the US FAA sponsored a worldwide database to anytime an engine failed, and so different companies bought into this, they would report them. So now we've got sources of data that help us understand when these problems arise so we can take steps to avoid them. Okay, my final example is another famous example known as the Ford Firestone tire failures. Now, Tim invited me to give this talk, and Tim was directly involved with this. In fact, he was the leader that helped solve the problem, figure out what went wrong. And Tim and I discussed a couple months ago after he invited me to give this talk. I said, gee, maybe you can come in and do this part of the presentation. And he said, oh, no, I'm going to let you do it. So I'll do my best here. Again, there's been quite a bit of documentation on this problem, but basically Ford and Firestone. So Ford manufactures, automobiles, trucks, and so forth, as everybody knows, and Firestone manufactures tires. And Ford and Firestone have been cooperating for decades, for being a key supplier to Ford of tires. But in the late 1990s, reports of tread separation failures began to come in. So again, here it is, just like the problem I told you about before. You have a product in the field, and then there's some early failures. That's what they were seeing here. Tread separation events can actually turn out to be quite serious because they can cause rollover events, where the vehicle rolls over, and that can cause serious problems, and indeed had caused serious problems. There have been 271 deaths from accidents due to tire failures in the US alone. And there had been even more if you look at various other countries where the Ford Firestone problems had arisen. In fact, the problems arose initially in places outside the United States where it was very hot, in the Mideast in particular, and then in Venezuela. That should have been a key that, gee, something's going on here. And to get busy and try and figure out how serious is the problem and what do we need to do about it. And again, is this just a few tires, or is this all of the tires? So it turned out that after they discovered this, they said, we've got a serious problem here, and a decision was made to recall 14.4 million tires. Once they understood the magnitude of the problem, the seriousness of the problem, and some of the root causes. So at about this time, Firestone was saying, oh, this is a Ford Explorer problem, and Ford was saying, no, it's a Firestone tire problem. It seemed to be maybe an interaction where they come together, but they really needed to get to the root cause and figure out what was going on, and that's what Tim did. So Tim led a group at Ford. The group consisted of engineers and statisticians that very carefully examined the problem. And they started initially with what we call field failure data. Again, you know how many tires are out there because you sold them, and you've got automobiles that are under warranty, so you have information even about the ones that didn't fail. But then you've got all these failures that occurred, and certainly they would have known about almost every failure that occurred because of the seriousness of these accidents. And also, not to mention warranty costs, but the seriousness is probably even more reason why all of these were being reported. So Tim and his group started out by looking at information coming from field failures. So here's the next 4 slides here come from a presentation that Tim gave that I found on his webpage, and he and I communicated. I asked, could I use a few of these slides in talking about this rather than try to reproduce it, because I don't have the data anyway. And Tim said, sure. And so he was very helpful in explaining some of the things to me as well, what happened. But everything I'm presenting is in the report that was that was put together to study this this issue, I'll call it. So again, when we wrote this up, we were very careful to only use stuff that had been published. What we can see here, this is what's known as cumulative hazard. So you can think of this as being like proportional to the number of failures that you might expect to see over time. And the three that are the worst here, if you can see the colors red, green, and blue, these are different Firestone factories. So it seemed that the factories are not all the same, but they were all bad. All of these Firestone tires were bad. On the other hand, when you look to the far right, you see what happens with other tires, the cumulative hazard estimated. So it's not nearly as bad. Again, the risk goes up after 5 or 6 years, but the risk is still relatively low. You can see how bad it is for those three factories. So here we're looking at some different data, again, from tires that had failed, and we're sort of trying to understand the root cause. So one of the so-called covariates that they had in their data analysis was the wedge size. And what they discovered was that when the wedge size is small, the probability of failure is higher. So you can look at the box plots here at the bottom, and those correspond to what we see here. And again, the one at the bottom, the red one at the bottom, has the smallest wedges, and those are the ones that are failing most rapidly in the field. And then on the other side, we have the blue, and again, the blue tends to have larger wedge. So that was pretty strong circumstantial evidence that this wedge size is important. And then when they looked at other tires, the wedge size was much larger. So these are not Firestone tires, or at least not Firestone tires from these three factories. It's not clear where those other tires came from, but they were not susceptible to failure. Again, going back and looking at the far right here and seeing the other tires. Okay, and here is looking at tire strength. So you can take tires that had not failed, and they had a lot of tires that didn't fail, but that had aged for a number of years. And then you can go in and do destructive tests on the strength of the bond. And again, you can see that the red ones at the bottom have the lowest level of strength. So it seems that the wedge size is related to strength. And you can sort of begin to put that together with knowledge of the physics of these failures. So we're getting close to the root cause, but it's still all circumstantial evidence. So what Tim said was, we need to demonstrate this cause and effect. Well, how would you do that? Because everything we're doing here has just been observational data. So what Tim did was he designed a big experiment. Now, interestingly, and I don't think the Firestone people realize this, Tim told me at one point, he said, at some point during this investigation, Firestone management told their people, don't talk to the Ford people anymore. Don't give them any information. You know, we might be at some risk here. So Tim was doing all this. Tim and his group at Ford were doing all this on their own. And Tim said, we need to design an experiment to demonstrate cause and effect here. And so that's what he did. And what Firestone didn't know was that before Tim went back to school to get his PhD, he had worked for Dunlop Tires as sort of a tire engineer. And so he knew what was going on here, and he knew how to run an experiment that could reproduce the failures they were seeing in the field. So I won't go into a great deal of detail, except that he's looking here at load, pressure, and ambient temperature, and different combinations of those. And sure enough, he was able to show how these relate to the failure event, and he was able to recreate the failures that were happening in the field in a fairly short amount of time. Okay, so what did we learn from what happened in the Ford Firestone? Well, careful surveillance of reliability data can detect problems early before they become severe. And this has led to warranty early warning systems that are now in place. And indeed, there was a mandate from the US Congress to set up a database. It was actually called the TREAD Act, like a tread in a tire. TREAD stands for something else. I can't remember exactly what it is, but basically it's when you have failures of critical things, it needs to go into a database. All manufacturers need to start putting this data together so we can detect these problems before they become serious. Proper statistical analysis of field data, like I illustrated that Tim and his group had done, can often point to what was going on, and then combine that with a careful experimentation, you can confirm the causes of failure. And the moral is you need to do more appropriate reliability testing up front before implementing cost-cutting changes. There's some evidence in the report that Firestone made some cost-cutting changes that reduced the wedge size, but they didn't test it sufficiently. If they had built a rig like Tim did and tested it, they would have said, oh, by doing that, we're increasing the risk of failure. But evidently they didn't do that. They made the change and it led to the disaster. Okay. These are the references from which I got all of the information. This may be too small for many of you to read. Now I guess you can read it on a screen without too much difficulty. So the first couple of references there are engineers that worked on the bell cells, and subsequently they published a lot of interesting things that gave a lot of the details. That actually was one of the problems where I was involved in the aftermath, because I was spending summers at Bell Laboratories between 1978 and 1992. And in the first 5 years or so, they were still trying to figure out exactly what happened and how to prevent it. So I was peripherally involved in that. And then the Wall Street Journal article. And then the JASA paper here by Sid Delau and others that did a very careful risk analysis that showed that the risk was much, much, much higher than even the engineers had feared. And then there's the NTSB report for the United Airlines. All these things are available on the internet. The Presidential Commission, so-called Rogers report for the Shuttle disaster. And then the National Highway Safety Administration report that very carefully studied the Firestone problem. And then there's a very interesting book by Dr. Wu that focuses on reliability disasters. And in particular, he's got one chapter that focuses just on reliability disasters. So I found that to be very interesting reading. And there's a lot you can read about on Wikipedia about these. So for example, there's a very interesting article for the United 232. By the way, United Airlines retired number 232. You'll never find a United Airlines flight 232 since then. Okay. Some concluding remarks. Reliability disasters are often caused by unanticipated failure modes, because if the failure mode had been anticipated, the engineers would have come in and say, we need to figure out how to keep this from happening. Another thing that I've seen is engineers tend to want to be conservative for good reasons. But managers often will ask, are we being too conservative here? And often it's because to be conservative increases cost or does other things that might be undesirable. You need to have an appropriate balance, and I would argue in some of the examples that I've shown here, the balance went in the wrong direction. And proper use of statistical and probabilistic methods is really important in reliability applications. And finally, some thanks to some of my collaborators and other colleagues who have provided information or provided feedback, I should say, on my presentation. So if there's any questions, I'd be happy to take them. I think I've left a few minutes for that. So is Kristen still there?
I'm still there. Like,
okay, I wasn't hearing you.